Hey, welcome back to Math with Patrick and Quill. Today is December 23rd, and we're solving problem 357 from the Daily Epsilon calendar. The answer today should be 23 because that's today's date. So we are proving the birthday problem. We need to find the smallest number of people with greater than 50% probability that two will share a birthday. And I think this means like at least two, or in other words, like it's totally fine if we come across a scenario where we have three people on the same birthday, or it's totally fine if we have two pairs. We're just trying to find, or just trying to guarantee that we do have a pair more than 50% of the time. And given that idea that there are different ways to succeed in this problem, different ways that we could have two people sharing a birthday, like we could just have a pair, we could have two pair, we could have a triplet and a pair. There's so many ways to have two people sharing a birthday that I think it's easier to think what's the probability of no one sharing a birthday. And that's what I'm going to explore first with a few simplifications, I suppose. In real life, we have a 365-day calendar, except for almost every 4 years, there is a leap day. There are some weird rules, like I think it's like every 4 years we have a leap day, but then every 100 years we don't, but then every 400 years we do. So there's really weird rules about it. Usually it's going to be 365 days, not 366. Maybe I might play around with the idea of 365.25 towards the end of the video, just to see if that changes the numbers at all. The 0.25 suggesting that one in every 4 years we come across February 29th. The next assumption I'm going to make is that the probability distribution, so the probability that we land on a given day, is uniform. I'm assuming that if we look at the whole calendar, here is January 1st, here is December 31st. We have a uniform probability distribution of what days birthdays fall on. And we know that's not true just because people have studied it. And I'm going to put a little image probably here, I think, that shows the actual true probability distribution. For example, you could probably see February 29th on there is really, really low because approximately 1 in 4 birthdays happen there because it only happens one in every 4 years. And then some holidays are also pretty low. I think that's because there are enough births that are planned through drugs or through surgery that certain days have a lower probability than others. So let's actually discuss that for just a sec because I'm going to assume that the probability distribution is uniform. But I think if we have a non-uniform distribution, that will increase the likelihood of birthday double ups. And I could prove this, or at least kind of demonstrate why I think this is the case with a coin toss. Let's say we have a fair coin toss and we toss a coin twice. We basically have a 50% chance that we double up on either option. However, if I have some kind of weighted coin where the probability of, say, heads is twice as likely as tails, I could think of this as my sample space instead, where I have twice the chance of getting heads over tails. And then now I can shade in the parts that have a double up, either two heads or two tails. And originally we had a 1/2 probability of getting the same outcome twice, but here we have a 5/9 probability of getting the same outcome twice. So in real life, given that we do have more probability of certain days, that would suggest that it is more common to get a double up of a birthday, and therefore this answer 23 might be decreased to 22. But then again, if we think about rounding down to 365, we're ignoring the fact that February 29th is a valid birthday, 1/4 of the time compared to other days on average. And so if we do round down to 365, and then thinking of a real world scenario again, we might come across a person with a February 29th birthday, and we would be like, oh, I didn't even consider for that in the math. Maybe this number would have to be higher. So I'm hoping that these two assumptions that I'm assuming for a uniform probability distribution and I'm also assuming that there's just 365 days in a year, I'm hoping that these kind of cancel out because the errors are going in opposite directions. Anyways, those are my assumptions, and let's get to it. So let's explore the possibility of no one sharing the same birthday. If we have one person in our group, there is a 100% chance that we have no double ups. We don't have a second person yet. I am going to express this as 365 over 365 because I think I'm going to find a pattern when I start looking at more people in our group. So when we introduce the second person, and I'm still thinking in the case of when don't they double up, um, I would basically just need to not pick the same day that I picked before. So I still have a 100% chance of not failing with the first person. And then once I try to put the second person in my set, I just need to make sure that their birthday does not land on the same day as the first person. So I'm going to multiply these two fractions because it's like I'm doing two successive probabilities. I'm assuming that these events are independent. I guess this is my third assumption. Technically, if I've already taken one person from the world, I'm decreasing the probability overall of getting another person on that same birthday because I've stolen one of those people with that given birthday. But there's also like 8 billion people in the world, so it's fine to assume that these are independent events. And then when I introduce a third person to the group, I will tack on just another fraction. The third fraction here is going to demonstrate that I can't pick two previous days that I've already chosen, and so that's why I'm subtracting 2 from the numerator here. And this is just our fraction pattern. We're going to have this long product. Let's do maybe n here to generalize it. We're going to have this long product of all these fractions. The denominator stays the same every time, so it's 365 to the power of, and then notice how a 3 matches here, 2 matches here, so I can confidently put 365 to the power of n on top, and then, or on bottom, or for the exponent here. And then in the numerator, we're getting this descending product, and so we could write this with a factorial. For this particular example, where n equals 3, I have 365 factorial over 362 factorial. This one is canceling out all the numbers from 362 all the way down to 1. Noting that these two numbers are 3 apart, I can use n in my expression over here, where we have 365 factorial over 365 minus n factorial. And this pattern holds true over here. Like for this one, I could have done 365 over 365 minus 2 factorial, because this covers canceling out all the factors from 363 all the way down to 1. And this is basically it. I don't really want to do these calculations by hand, so I'm going to hop on over to Desmos really shortly, but I will just port over this expression and we can test out different values for n. So I had a little trouble with Desmos here. Here's the expression that we created on the whiteboard. But when I try typing it in and then plugging in different values for n, ignore this guy for a sec, it just says undefined the whole time. And that's just because Desmos is kind of yelling at me for telling it to compute these really, really large factorials. So like if we try doing, say, like 3 factorial over 3 factorial, it just gives me the number 1. But then 30 factorial, see how big that number is? It does know that it's the same number on top and bottom, but once I get to 300 factorial, or somewhere between 30 and 300 factorial, it just kind of gives up on me. So this expression doesn't really work here. And instead, I wrote this expression here. We can just use this capital pi to do a successive product. And so each term is going to have a 365 in the denominator. It works like sigma notation, where we start when I is equal to this bottom number. So I'm looking right here and pretending that I is equal to 1. And then if I do 365 minus 1 plus 1, that plunks this 365 in the first numerator. Then I'll multiply by the next thing when I is equal to 2. I'll be subtracting 2 now instead of 1. So overall, I'll be getting a 364 in the numerator. 365 stay the same. So if I do I equals 3, this product expression will get the same value down here. And ideally, this expression up here would have had the same number. It's just that Desmos is calculating those factorials first, and these numbers are getting way too big, way too quick. And then we do have to remember that this is the probability of us not finding a birthday match with 3 people. So I need to do 1 minus, because this is taking the probability of not finding no birthday matches, or in other words, finding at least one birthday match. So here, now we can see the probability is really, really low, like less than 1% when we have 3 people. And hopefully as we tick this number up, we will eventually hit 50%, or I guess the problem today wanted us to hit above 50%. So we can see that the probability is climbing, 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 and then right here, once we hit n equals 23, we do crest 50%. Now, I think it'd be interesting to now try to plug in that 365.25. Let's see if this actually changes the value all that much. Not really. The first 3 decimal places are the same, and then our 4th decimal place is only off by like maybe 2 thousandths or 2 10,000ths there, so not much. And then if we tried the kind of the upper bound idea of just plugging in a 366, just assuming that the leap day birthday is as common as the rest, we still do get a value over 50%. And then it is definitely below 50% when n is equal to 22. So the kind of like real life changes due to different probability distributions and leap days or not doesn't really seem to affect the outcome, where it's still hovering just over 50%. And then it doesn't seem like we can really get this thousands place to really move in a way that we would get something below 50%. So I think that means we're all done today. N is equal to 23. That's what makes this probability greater than 50%. And we're all done. So thanks again for sticking around. Here's Quill again, a little reward for you at the end of the video. And I'll see you tomorrow. Bye.